Sir, good morning, sir.
Sir, good morning.
Good morning, sir. Good morning, sir. Yes.
So we'll wait 1 or 2 minutes, then we'll start, sir.
Okay, no problem, no problem.
Sir, shall we start, sir?
Sure, sir. We can start. No problem.
So, good morning to the today's speaker, Mr. K. Bhupati, Director and Division Head, Research and Development, Resource Data Analytics and Forecasting and Solar Radiation Resource Assessment from National Institute of Indian Energy, Chennai. So, sir is going to deliver a talk on design and modeling of wind turbine and challenges. So, let me introduce the today's speaker, Mr. K. Bhupati, sir. So, sir is graduated in mechanical engineering and received master's degrees MTech both in energy as well as in footwear science and engineering. And sir is also pursuing the PhD and also worked as faculty at Engineering College and VIT University. After that, sir joined at National Institute of Indian Energy in the year 2003 and dedicated to assess the wind resource potential of India at a 50-meter height and successfully published for the public. Prosperously lead wind resource assessment unit as a head of the department from February 2012 to April 2017. So successfully launched the nation wind power forecasting project and received Scotch Award in 2016, e-governance award in 2019, best forecasting award in 2019, and merit order award for solar power forecasting. And successfully developed a 50-meter, 80-meter, 100-meter, and 120-meter height wind atlas and published. And providing a consultancy for leading government organizations, public sectors, and private organizations on wind farm design and development. And involving in various research activities such as offshore wind profile measurement, wind characteristics, study in complex terrain. And looking after R&D, data analytics and forecasting, solar radiation, resource assessment and renewable energy projects. And sir also published many papers, research papers in wind and solar energy. So with this, I request Mr. Bhupati sir, please deliver the lecture.
Thank you, sir. Yeah, thank you, sir. Thank you. First of all, I would like to thank for inviting me to give lectures on design and challenges of wind turbine. And also, I would like to thank for our management and for all the participants on behalf of the participants. Also, I would like to thank. I hope I will deliver the lectures without make you too sleepy. I hope. Okay, sir. Yeah. So yeah, just I'll mute my video because sometimes the streaming may not be good. Yeah. One moment. One moment, sir. I'm sharing my
Yeah,
PPT.
sir, please share, sir.
It's not able to share. Sir, you have disabled screen sharing.
Yeah, already enabled, sir. Please.
Now host disabled participant screen sharing. 1 minute. Huh? Now it's okay. Okay, sir. Yeah, it has come back. Sir, can you see now my screen?
No, sir.
Not it share?
It is not shared.
Okay. Now it's sharing, sir?
Now it is sharing.
Okay, okay, okay. Perfect, perfect. Thank you, sir. Yeah, thank you. Let me start. Yeah, so I'm very happy to be here to give lectures on design and modeling of wind turbine and the challenges. So whatever the thing it is there, I will give the overall view how to design, what are the principles behind of design of wind turbine and what are the challenges are behind the wind turbine design. Just I will explain to you. So this is about me, and I also would like to thank for sir for giving me the grateful introduction about me. Okay, then design. So design of wind turbine. So what you do, whatever the things you want to design, what you will do first. First things what you will do. Just for imagine it, whatever, because you are the most of them are, sir, all of them are from mechanical engineers or others also there, sir?
Others also there, sir.
Others also there. Okay.
Electrical engineers.
Yeah, electrical, mechanical, and what are
Civil.
the other? Civil. Okay, okay, perfect, sir. So you know that, so design. So whatever the things you want to design, what you will do first? Simply you will straight away go and design it? No, you will do the lot of basic process work, right? So then I will explain one by one. The first thing is the wind turbine design. So wind turbine design is that is a process of defining the form and the specification of a wind turbine. Why do I want to design? First thing is that we want to know what is my output it is going to be there. Here my wind turbine design is my output is to I am going to extract energy from the wind. For this I am going to make some process which define the form and the specification. So that is the process of that is a design of that is a wind turbine. Okay, so design, can I straight away go and do the design? It is not at all possible. I need some standards. So I have to follow the standards. Each country, they're having the different standards. So then we have to follow the standards. Okay, then wind energy design is not that is a new technology, but it has been using, since 2000 years before. because the wind energy has been used for various purposes like sailing, say I mean sailing say sailing boats, ships, and draining rice, and water pumping, and various other purposes have been used. Okay, the mostly some of them are saying that in 200 BC they used China, and 5000 BC in propelled boats and Danish scientists. But the modern wind turbine, it was developed in 1896. Okay, so the current practice of wind turbine design. The first things I told you, what we want to do, current wind turbine design methods. First is the conceptual. What is the conceptual? What you want to do it? First, you will have it in my mind. That is, am I correct? Because whatever the things you want to design, first what you will bring into your mind. Oh, this is the things I want. Then you will make the process. Then what you will do, you will add that is a number. So without the number you cannot do it. And how much the load it is going to act on this one. And now for the particular, for the wind turbine, we need the control algorithm, so that it will control the wind turbine in safety and protected manners. And structural design, then we have to do that is a structural design and analysis. Then machinery components, various machinery components are there in the wind turbine, and do the assessment of the design, whatever the design you have done it. So without doing the assessment, it is not at all valid. And also then finally next to only, then you will do the detailed engineering. So detailed engineering to give the complete details of what is the size and the shape, what are the diamonds and everything, it will be given. Next, after detailed engineering, you will do there is a prototyping. After prototyping, you cannot go and install your wind turbine in the field. Then we have to do the testing and the certification of the wind turbine. This is That is the overall process. Then before starting this one, you should know about what is the wind turbine and the basic components. So the last class, I know how many of them have attended, and the some of the components I have given that I had given the basics of fixing. And here you before designing of wind turbine, you should know about what are the different components and their functions. So then only we can design it. Okay, then basics. So the wind turbines, you know that. So wind turbine, it is a rotating machine, correct or not? It is a rotating machine which captures the wind. So which captures wherever the wind is coming there, just which captures the wind by means of that is a aerodynamically designed blades. I will explain to you. There is a aerodynamically designed blades and converts into rotating mechanical power. This entire rotor, with just it's rotates and it's converts into it's a mechanical power. Then mechanic power is then taken up at the shaft. Here I'll explain to you. Here you have the shaft. The shaft in the form of the movement at a certain rotation, and this it is transferred to a machine. The entire wind power, the entire wind turbine, which consists of rotor. I mean the rotor means there is a blades and hub and gear, mechanical gear and generators. Okay, fine. So the wind turbine, when you want to design it, what are the basic requirements? The requirement is it should give that is a low cost of electricity, correct? So that is our main purpose. Whatever the thing is there, whatever you are designing there, finally where you will stand, economic, whether it is economically viable or not. It means that you should give that is a low cost electricity. Okay, now currently you know how much you are paying for electricity to for your domestic purpose. Maybe that depends on the unit you are consuming it. In Tamil Nadu, in case if you have consumed it less than 100 units, there will be no cost. Then if it is greater than 100, I mean 100 to 200 units, some rupees, I think so 3 rupees something. They are, I mean 2 rupees 50 paise. Then the 200 to 300 units, they are saying that is 3 rupees 50 paise or something. It's keep on it goes. If it is greater than 500 units, they will charge 6 rupees. So like this there, it means that low cost electricity it has to be produced, and also energy at utility scale. Wherever you are having it at utility scale means the large numbers. I mean the large scale it has to generate electricity. And high availability. What is the high availability? Availability means it should be always available to generate power. So that is the way we have. That is the way it's required. And also the survival, because the wind turbine it's going to be there in environmental condition. Environmentally, you know that it's a nature phenomena. So nature phenomena we cannot predict properly. I mean we can predict in certain level, but it has to work. It has to survive with that is for earthquake and for lightning and for storm and various the extreme condition it has to survive. And minimum, that is environmental impact. Environmental impact should not be there. That is our basic requirements of the wind turbines. Okay, so this is the schematic diagram which shows that the conversion of energy in the three major areas. One is the aerodynamic conversion, then mechanical energy conversion, and the electrical energy conversion, right? So the aerodynamic principles. So the aerodynamic principles are used to convert the linear flow. Actually, the wind is, that is a linear flow. Wind is, that is a linear flow. The linear motion is converted into, that is a rotary motion by the blades, that the previous slide I had shown. This is the linear flow of the wind. The linear flow of the wind is converted into rotary motion. You see that the blades which rotates. So that is a rotary motions. Okay, see the rotary motions, in terms of, it's of the torque. The efficiency of this aerodynamic conversion is determined by blade profile. I'll explain to you blade profile and angle of attack of the wind turbine blades. So that is defined by, that is the efficiency, that is called, that is the aerodynamic conversion. This rotary motion is converted into, that is kinetic energy. That is the kinetic energy of the wind is converted into, that is a mechanical energy. So mechanical energy in terms of torque, right? So this torque, this mechanical energy will be converted into electrical energy by the generator. So this is the basic principle of wind turbines. So now we can see there is a component. There are many different components are there. There are more than 8,000 components are there. Out of 8,000 components, these are the major components. That's called the rotor. That is a blade and hub. This is called the hub. That's a rotor. These are the drivetrain components, and this is a tower and the control system. We have the two types of control system. One is on the top of the nacelle and the other one is the bottom of the tower. We have the control system. Yaw system, that is the how the entire turbine moves towards the wind direction. In case the wind is coming from this direction, the entire rotor will face towards the wind direction. In case the wind is coming from this direction, the entire rotor moves towards this direction. So this is called the yaw system, and the mainframe which supports the entire component, and the nacelle. And I'll explain to you one by one what are the different components are there. So that what we have seen, that is a major component, and other subcomponents also it is there. So we have seen the tower, blades, okay, blades, one, two, three blades, and hub, right? And pitching system. So pitching system which consists, I mean, it is having the inside the blades, right? It between, I mean, inside the blades, right? Yaw system, then main shaft. So this is called, that is the main shaft, because it is attached to the hub, and it is attached to the rotors. And yeah, next, that is a gearbox. Here we have, that is a gearbox, and the coupling. So coupling between the generator and the gearbox, you have the coupling, and generator here we have it, and mechanical brakes, and also aerodynamic brake, and control system, converter, and mainframe, and the sensors. Many sensors are there, and hydraulic system, cooling system, and others. Okay, these are the components, right? The rotor. So this is called, that is a nacelle. This is nacelle. So the all the drivetrain components, okay, all the drivetrain components like shaft, gearbox, generators are placed on the top of the tower. This is called, that is a top of the tower. Top of, I mean the top of the tower. Okay, top of the tower, above which we have placed our nacelle. So the nacelle, this is the entire, the entire section is called the nacelle. So the nacelle which protect the drivetrain components from the environment, right? So that is so yeah, I mean the rotor which comprises of blades and hub. Okay, the blades, how many blades are there? There are three blades, one, two, three. It depends. Okay, depends on the turbine. We may have the three blades, one blades, or two blades also. It will be there. And this is the hub, right? So here, what is the purpose of the rotor? The rotor which transforms the energy contained in the wind. I have told you already explained that it's a linear motion of the wind which is coming from there. And so, okay, then it will convert into rotary motion. It means that it transforms the energy contained in the wind into mechanical rotation. It is referred to as this is called, that is a rotor, right? So it consists of, several rotor blades and the rotor hub. It may be the one blade, two blade, or three blades. And here we have the hub, and inside we have the blade pitch mechanism. Okay, so this is the rotor blade. Now you can see that it's a rotor blades. Okay, so this is the blades of the wind turbine, have the aerofoil sections. So what is the function of this aerofoil? I mean the blade, which it captures the energy from the wind and transfer its power to the hub. Previously, you can see there, it captures, I mean the blade, the function of the blade is it captures the energy from the wind. Okay, and it transfers the power to the hub, right? Right. Okay, the hub, the blades. Now we can see the blade which has that is a circular cross section at the root. This is called the root, circular cross section of the root, and have thicker aerofoil blade section. I mean in this section has the thick, thick aerofoil cross section, and slowly it reduces the aerofoil section, and the end of the blade which have that is a thin, thin aerofoils, right? This is called that is a thin aerofoil sections. We have it in this blades, and you can also see here. So this is called that is a aerofoil sections. You know that the mechanical engineers might have studied, mechanical and civil engineers might have studied there is a aerofoil section. So this the wind turbine blades in almost similar to your the aeroplane wings. Okay, so when you cut the blades, when you cut the blade, you can see the section of the blade. The section of the blade is that's called the aerofoil section. Okay, this is called that is a aerofoil section. The entire blade is that is a aerofoil section blades. Here you can see the blades. You can see the blade here. It's a tappers in cord. Tappers in cord. So cord means that is a line joining between the leading edge and the trailing edge. So when you are joining the line between, this is called the leading edge. Oh, sorry. When you are joining line between, that is a leading edge, this is called the trailing edge. This line is called as the chord line. Okay, you can see the chord. It's a tappers in chord. Just you can see the tappers in chord, and also the blades are coned outwards to tower clearance. You can see that is a coned. Okay, it's a coned outwards towards for the tower clearance, because it should not touch while it's rotating. It should not touch on the towers. Okay, and also very thinners. And you can see, oh, this is the modern blades, have that is a circular root section, and gradually changes its thickness of the aerofoil. Okay, aerofoil. You can see there is a high thickness here the aerofoil, and slowly it is reduces the aerofoil section of the blade. Now you can see you can just compare these are the blade components. What you can see, how it is flying. Is it from the natural phenomena? Yes, it is from the natural phenomena also. Now just look at here is the bird wings. How the birds can fly because of the aerodynamics. You might have seen that many number of birds, the flock of birds, it's flying together. It cannot fly. It cannot fly in a row, but it can fly in a, the shape of this aerodynamics. Can you see there? Aerodynamics. Daily we are using our, the two-wheeler, four-wheeler. Just look at that thing, and also look at your helmet. Is it aerodynamic shape? Yes, it is an aerodynamic shape. Many of the things are its aerodynamic shape, because it has to tear the wind. Okay, now just you can see that one bird will move. It lead the entire team of entire flock of birds, and other birds will fly in this direction, because of, see, once this bird gets, because of it has to tear the wind. So once this bird gets tired, then it will go back. Other birds will come moving. So this is the way the birds which can move and longer distance. Why I have to say here? So how it can fly? Because it has this aerodynamic effect. Just look at the wing, how it is purely as aerodynamic, and also just you can see the bones. Okay, here the bone. The structure is also the blade, wind turbine blade structure is also almost the same shape only. It is the aerodynamic shape. You can see, you can compare with this also aerodynamic shape. And for giving the strength of your strength of the bird's wing, it has the bones. Here it gives the strength of the blade. It's the hollow shape of the blade, and to give the strength of the blade, here the spar rod, right? The spar rod it will be there to give the more strength of the blades, right? And also the shells and the various cells are there. These are the wind turbine component. This is the circular root section, which has the circular root section which has the bolts. Previous one you have seen, you can see the this is the bolt. So this bolt will be fixed on the hub, right? So this is called the hub. What is the hub? What do you say? What do you mean the hub? It is a general term. Hub means just it's a connecting. Here it means that the hub which connects the three blades and to three blades to the shaft. The shaft will be at this portion. It will be the shaft will be there, and also and some of the blades. Some of the technology of the turbines. The blades are firmly fixed on the bearings. Okay, I mean the bearing which connects the blade and hub. And some of the technology there will not be bearing in this one. So the bearings which the blades which does not have the bearing called, that is called the stall controlled machine. Stall controlled machine. The blade, the blades which connects the hub through bearings is called, that is the pitch bearing machines. Pitch, that is called the pitching. Pitching will happen here. So this is called, that is the pitch bearing machine. That the blades. The blades are usually made up of various materials like called glass fiber reinforced plastic, GFRP, fiber reinforced plastic, or polyester. Fiber is, that is the glass fiber. Glass fiber is, that is fiber is very, our hair like structures will be there. So they will place it. They will place it in the mold according to the requirements of the strength. Fiber. This is called the glass materials, and the fiber is this the fiber reinforced polyesters. The polyesters will be reinforced. That is the resin. Resin will be reinforced. Okay, once they have given the resin, then reinforced. Once it's become dried, it become, that is a solid material. So that's why it's a glass fiber reinforced plastic mostly they use, and many other materials also they will use it, because it depends on the strength requirement. And also we can use carbon fiber, but carbon fiber is little costly, too costly for manufacturing process. Okay, the drivetrain. Now just look at here. Here we have seen the turbines, right here. Yeah, so the turbine, the inside we have the drivetrain components. What is the drivetrain components? Okay, yeah, so the drivetrain components. Now look at here, this drivetrain components. The rotary motion of the turbine rotor. Here you have the blades here. Blades are connected. One, two, three blades. Okay, this because of its extract energy from the wind, and it should start rotating, right? So the rotation has to be the rotary motion has to be transmitted to the generator by means of mechanical transmission, called the drivetrain, right? So I have told you here we have the turbine. It extracts energy from the wind. It should start rotating. This rotary motion has to be transformed to the generator via the mechanical drivetrain. So this is called mechanical drivetrains. It consists of shaft, low speed shaft, and high speed shaft. Then it's the gearbox, right? These are the mechanical components. There's a shaft. Just it's simply it transmits the torque from the torque from the rotor to the rest of the drivetrain. This is called, that is in the low speed shaft. And why it's called the low speed shaft means it rotate at 10 rpm. For example, whatever the rotor rotates is the shaft also rotate at the same rpm. That's why it's called the low speed shaft. And high speed shaft is between the gearbox and the generator. It's called that the high speed shaft. And the high speed shaft will rotate at 1000 to 1500 rpm according to the requirement of the generator rotors, right? This is called the rotor. That is the gearbox. So generally the turbines rotate as a 10 rpm. The generator needs a 1000 rpm. In between we need the gearbox. So the gearbox, the ratio by 10 by 1000, it means that 1 is to 100. So 1 is to 100 depends upon either I can use that is a parallel shaft gearbox or planetary type of gearbox. So the mechanical engineers know that. So parallel shaft gearbox means this is the parallel shaft. So all are all gears. The gears input gear and output gears are parallel to each other. That's why it's called the parallel shaft gearbox. But the parallel shaft gearbox, we have to increase the number of stages. So 10 by 1,000. So 1 is to 100. 1 is to 100 time, I have to increase the speed. Then I have to design my gearbox according to my requirement. How many number of stages it's required. If in case if we have there is a more than one stages, then increase the bulkiness. Then what you have to do? Then you can go for that is the planetary gearbox. So we can reduce one third of the size. One third of the size can be reduced by using there is a planetary gearbox. And even that the planetary gearbox are there's the coaxials, right? It's not in the parallel, but it's a coaxial. The size can be reduced. And here the disadvantage is it is it will generate enormous amount of heat, right? So that is there in a planetary gearbox. The advantages, other advantages, depends on the operation. Whether you want to smooth operation, then we'll always use that is gears, that will parallel gears. The parallel gear depends on the stages, number of stages. So initial stages, the first two stages may be used the planetary gearbox, and the last stages will be used that the parallel shaft gears. Okay, so that is the way then it will be used in the gearbox. And a braking system. We need always a brake. How you are going to apply the brake? Why you want to apply the brake? Because we need to stop the turbine or limit the speed. How I am going to limit the speed? Either I can use that is a mechanical brake. So mechanical brake, just like a car brake, you have the disc brake and the normal drum brake, disc brake. Difference are there. When you are applying the brake, the pad will go against the wheel, then it can slowly stop your vehicle. The same way also here we can use it. Other way is that is the aerodynamic braking system. Aerodynamic braking system, either aerodynamic braking system, I told you previously here, in order to control the speed of the turbine, right? So here the blades are connected to the hub. You can see the blade are connected to the hub via the bearings. Okay, so that what will happen, the blade can rotate its own axis up to 180 degree, it can rotate. So it can rotate its own axis. That's you have seen here. Now you can see the blades can rotate its own axis, right? So because of it has there is a bearings. That is the purpose of, that is a braking, that is called, that is a aerodynamic braking system. There are two different types of aerodynamic. That is I told you, stall controlled machine and pitch controlled machine, right? So pitch controlled machine. So stall controlled machine, there will not be any bearings, but pitch controlled machine which will have the bearings and the main frames. So the main frame is the platform which the other principal components are attached. You can see this is the main frame. So the main frame, the purpose of the main frame is to give the support for all other drivetrain components. All the drivetrain components are placed on the the platforms, right? So it gives the proper alignment among those components, right? Next, the coupling. So the coupling is just couples between generator and the gearbox. The generator, the gearbox. So the generator needs a 1,000 RPM, right? And the gearbox output also will be the 1,000 RPM. 1,000 RPM. In between, we need couplings. So it should be always the flexible coupling, or because if there is a small misalignment, it is there, and simply just it will break, right? It will damage the shaft. In order to avoid such things, mostly they will use fluid coupling, or it is a flexible coupling, it will be used. Yeah, so this is the coupling. And generators, the last time also I explained to you about the generator. So the generators, either it may be that is asynchronous generator or synchronous generator, right? So mostly, so the generator which has the both yeah, one moment. So generators, the last time I explained to you, it's both. We can use as asynchronous generator, asynchronous or synchronous generator. So here, both the synchronous and asynchronous generator has the stator and the rotor. Okay, here the both generator is always connected to the stator, which is always connected to the grid. If there is no grid, there is no generation of the power. So it is always connected to the grid because initially it draws power from the grid, it acts as motor, and once we have that is a generator. Okay, so here the generator is coupled with the shaft. Shaft means that's a gearbox shaft. So gearbox shaft is connected with the rotor. So when the rotor speed is more, I mean the when the wind is more, automatically what will happen, it generates the power from the wind, power from the wind, and to push the power to the grid, it will go opposite direction. See, initially it draws power from the grid. Once it's, once we have that is, more power from the wind, then the rotor will push the power to the grid, I mean the through wire to the stators. That is there. Yaw drive, I explained to you, this is the tower top, this is the tower top. Okay, so yaw drive. So whenever the wind direction changes, always the rotor moves towards the, you can see, it can rotate at 360 degree. It can rotate at 360 degree. When the wind comes from this direction, the rotor moves towards this direction. When the wind comes from this direction, rotor moves towards this direction, so that it can increase the efficiency, so that it can extract maximum energy from the wind. And now you can see the tower. So what is the purpose of the tower? Just the tower, okay, it rises the turbine up in the air. Okay, so why you want to do it's the last, I mean many of them I attended the last class, because the wind speed increase with the height. That's called, that is the wind shear. So wind speed, this is the wind speed and height. You can see at low wind at low height, 10-meter height, I have the 5 meter per second. At 50-meter height, I have that is 8 meter per second. At 100-meter height, 100-meter height, I have the 10 meter per second. Now you can see. So, and also I have explained to you that is the power is equal to half rho A V cube. That is the power is directly proportional to the V cube, right? So when I increase the height, I can also increase the power. Extra, I can also extract the power, maximum power from the wind. So that's why then we have to rise the turbines in the air. So that is the purpose of the towers, right? So various different types of towers are there, and also the foundation. So the foundation, that is other most important component of this is must be sufficient to keep the turbine upright. Always you should keep it upright, right? Whatever the wind, whatever the external condition there, doesn't matter. You should keep up the turbine upright. So that is the purpose of the turbine. The electronic controller. There are many computers. This control system which has, there is a many number of computers. This computer which controls the entire turbine. Why should we control the turbine? Is there any purpose? Why let it run? Because the purpose is at a low wind speed, it has to try to extract maximum energy from the wind. At the high wind speed, it is there, it has to limit the power, right? In case of the extreme external conditions are there, like all of a sudden you have the storm, let the turbine will generate the power. You should not, because the extreme condition, we do not know that how much the turbulence it's going to be there, and also the direction suddenly it will change, at a different direction also it will change. Then at the time the turbine, we have to stop the turbine, and also we have to limit the turbine power also at a certain meter per second. So generally for 25 meter per second it has to stop. And also it will, the control system, it obtain the power from, that is various it can get the information from the various instruments which are fixed on the turbine. For example, the gearbox. The gearbox, then the gearbox just the oil. The oil temperature should not cross more than 80 degree. If it goes more than 80 degree, then it will keep on check, it will give the alarms and locks. If it is goes beyond certain limit, then what will happen, automatically it gives the information to the controller. Now I have crossed, the temperature is 85 degree. If it goes 85 degree centigrade, my oil will become thin, right? My oil will become thin, and the gearbox 1 to 1, when the gear it is 1 to 1, when it's meshing, then it will become wear and tear will be more. Then I want to avoid such a condition, then automatically give the signal to the control system. The control system will stop the entire turbine. After getting cools, then it will return back. So that is the purpose. So that is the control system, right? So now yeah, so the wind turbine, now I explain to you also this one. So the wind turbine, it's a device which converts mechanical energy into electrical energy. I told you that is the power is equal to power available in the wind is equal to half rho a v cube. It is the power available in the wind, but the power developed by the turbine is that is equal to P is equal to half rho a v cube into Cp. Cp is nothing but that is the power coefficient. This power coefficient is nothing but that is the how much it's the power extracted and what is the maximum power available in the wind. Okay, so this is called that is the power coefficient, but it has been derived. Okay, that the maximum power can be extracted from the wind energy is only 59.3 percentage only can be extracted. You may ask the question, why it is only the 59.3 percentage? Why can't we go for 100 percentage? Because yeah, I'll explain to you. So now this is called that is the power available in the wind. Power available in the wind is half rho a v cube. Power developed by the turbine equal to half rho a v cube into Cp. Cp is nothing but is the power coefficient. The power coefficient depends on the mechanical efficiency. Mechanical means in the gearbox efficiency and the electrical efficiency. The rotor efficiency, the maximum energy can be extracted by the rotor is only 59.3 percentage. But your electrical efficiency may be, I mean, the generator may be 95 percentage, gearbox may be 97 percentage, right? But the rotor only can extract 59.3 percentage, right? So this is, and some of the turbine also we can decide the direct drive. There cannot be any gearbox. The previous design we have seen, that is, components, that is the kinetic energy of the wind and mechanical energy, we have the gearbox. But here there is no gearbox. Without a gearbox, how it is possible? Because, the rotor which rotates at 10 RPM, right? My generators need the 1000 RPM. In between, I need the gearbox so that it can step up the speed 10 RPM to 1000 RPM can step up. In case if there is no gearbox, what will happen? Now we have the formula. So F that is N is equal to speed is equal to 120 F by P. Normally the synchronous I mean the asynchronous generator, the number of poles, okay, so the poles will be 4 or 6. That I think so you might have studied the poles. What is the number of poles? 4 or 6 will be there. And the frequency in our country, the frequency 50 hertz, and number of poles it is a 6. For example, 120 by 6 into 50, right? The 6, that is a 2, 20. So 20 into 50, that is equal to 1000 RPM, right? In case the number of pole is 4, that is a 1500 RPM. It is know that. Okay. So now can we reduce? Now there is no, I mean, can we just increase? There is a number of poles. And number of poles. These are all constant. 120. 120, that is a 3 into 120, that is 360. That is a total. Right, 120, 120, 120, that is a three phase, right? So that is a 120 degree each. So 120 degree each, then that cannot be changed, hence cannot be changed. Number of poles can be changed so that the speed can be adjusted, right? So based on this mechanism, we can avoid the gearbox, then we can directly connect to the generator. But here in this type of generator, the generator number of poles increases, and also the size of the turbine also will increase, size of the generator also will increase. But the thing is that since there is no gearbox, the size of the entire nacelle size also can be reduced from this kind of the turbines, right? And the wind characteristics, the wind is it is in what is called variable in nature. So variable in nature means it will vary from time to time and place to place also. Every second it will vary. Now you can see here, just it's the time of 1 hour, and how the wind speed you can see that it's reduce the wind speed and increase the wind speed. Okay, it will vary from place. I mean, time to time also it will vary. Every second it will vary, right? So this is the universal characteristic variability, and its dispersion are dominant consideration for any wind power system design. So the turbine has to be designed to work with this variable nature of the wind. So the wind characterizes distribution over the swept area of the blades, and amount of turbulence are existing in the wind turbines. So now you know that. So now just I have given that is the overall view of the components. Now this are everything is coupled. Wind, yes, it's coupled because of the wind. And aerodynamics, I have explained to you. So the aerodynamics, the blades, I have explained to you also. So this aerodynamics of the blade, right? So when the wind is hitting on the surface of the blade, you can see there is a many number of aerodynamic blades are there in the blade. So when the wind hits on the blade, it's working basic principle of that is a Bernoulli's principle. When the wind is divided into two portion, upper portion and the lower portion, the upper portion will have that is the high speed and low, I mean the high speed and low pressure, and the bottom region will have that is a low speed and high pressure. So you know the basic principle, the high pressure region always try to move to the low pressure region, then automatically since it's happening of the entire blade starts its rotating. So that is aerodynamic and blade dynamics. I mean that's always it's rotating, and the control system, drivetrain, electrical network, tower, foundation, everything it's coupled. Okay, so the wind turbine generators are, I told you, it is a large rotating machines coupled to the wind with its fluctuation. Okay, and also since it is the fluctuation of the wind and also the torque, also the variation, I mean the torque variation also will be there. Since the torque variation is there and also your power variation also, I mean the fluctuates. Your frequency and voltage always will, it fluctuates. Then you have to design the wind turbine based on these conditions, and also in the various complex engineering challenges. Okay, so then when you want to design the wind turbine, the first thing is that be safe, reliable, and and competitive price. And these are the major challenging of engineering work. And also the turbine has to be designed for high turbulence. Because I told you that the wind is that is a natural turbulence, right? It is which has that is the turbulence. It has to work with the turbulent nature of the wind and high cycle fatigue. And since it is a continuously rotating, which has the high cycle fatigue and varying the drivetrain loads, since the variable nature of the wind, the drivetrain loads because of the rotor will rotate and depends on the wind speed and resonant of dynamics and high reliability and wake interactions. What is that? I'll explain to you the wake interactions. So this is the power curve. What is the power curve? So power curve, the wind speed. This is the wind speed versus power. So I mean designer will give based on the design of the wind turbine. He designed and what power he will generate at what wind speed. Then based on this one, I have already explained to you. Power is equal to half rho A and V cube into C. That's the turbine powers, right? So now power available in the wind. This is then power how much it's going to generate. This is the 1500 kilowatt turbine. How it will generate for each wind speed. Now I have designed at 11 meter per second. My turbine can generate 1250 kilowatt. 1250 kilowatt. And for in case increases at 13 meter per second, my turbine can generate 1500 kilowatt. 1500 kilowatt. Right. Yeah, so this is the wind speed distribution and the power curve. Just look at here. That is the wind speed, how the wind speed is distributed along with the power curve. Right. See here. So I told you the power is directly proportional to the V cube. Since the power is directly proportional to the V cube, what will happen now? Just look at here. Just look at here. It will keep on increase. That is the wind shear, na? Because that is the power is proportional to the V cube. Correct. This is the wind power. So the wind power just it will keep on increase. But here, just look at here, there is a power curve. Okay. So that power curve, this is the stall controlled machine. This is the pitch controlled machine. I will explain to you also stall controlled machine. There will not be any bearings between the hub and the blades, right? So this is the blade. Here I have the hub. There is no, there is no bearings between the hub and the blades, right? This is the stall control machine. Now I have to limit the power. The purpose of this mechanism is to limit the power. You can see here when the wind speed increases, when it reaches the rated power, the rated wind speed, that previously I have seen there. So this is called, that is a rated wind speed. At the rated wind speed, it means that I have designed my turbine at 13 meter per second, it has to generate 1500 kilowatt, right? So that is called, that is a rated wind speed. So I have designed, it is generating 1500 kilowatt. And also here also, it has been designed at 13 meter per second, both the pitch control and stall control machine, it has to generate the rated power of 1500 kilowatt. But if the wind speed increases, when the wind speed increases, the stall control machine is stalling the turbine. It means that power is reduced. Why this? Because I have to reduce the speed of my turbine. It is a control mechanism. You have to design the control. It has to, it has been designed. The control mechanisms to limit the power of the rotors. Then automatically, once they limit the power, automatically reduce the power, and when the wind speed is reduced, automatically it will go back to that is a normal position. And for the pitch control machine, since the hub, since the hub which is connected to the blades by bearings. Here I have the bearings, right? So since it has the blade bearing, the blade can rotate its own axis so that it can adjust the blades angles. So that is the angle of attack. So I have, explained to you also. So this is the blade, right? This is the chord line. Chord line is connecting the leading edge to trailing edge, and this is the wind direction. The angle between the wind direction, that is the wind, and the chord line, that's called the angle of attack, right? So this angle of, when the angle of attack is adjusted, so that it can always maintain the power at a constant, that is 1500 kilowatt. You understand or not? So it will maintain the constant power. Even the wind speed increases, the power also it's a constant. Up to where? Up to 25 meter per second. When it reaches the 25 meter per second, my entire power, it will be stopped. It means that my turbine will be turned off, right? Then it will be bring back to, that is a normal conditions. Okay, so then what I have to say here is that is the power curve. What it says, that is a pitch controlled machine. Now you can see the power available in the wind is this much frequency distribution. So this is the wind speed is frequently distributed this much, and the power is just, you can see here the power is here. There is a power curve is there, right? So comparing the power curve and the frequency distribution, we can see that the turbine operates at its rated output. So here, what is the, this is the 2300 kilowatt turbine. Okay, so the turbine operates at the rated output of 2300 kilowatt, around only 8% only. Okay, so from this graph, what you can understand from here, can rated power can be there only 8% of the time. 8% of the time. So 8 by 100 into per year we have 8760 hours. So now just one moment. Yes. Now you can see 8760. You can cancel this zero, and zero point 0.8 into 876. If you multiply this many number of hours only, you have, that is a rated wind speed. All other time you have less than this. And also mostly 50% of the time there will be less than 3.5 meter per second. Okay. So it can start. This is a 3.5. Okay, at 3.5 meter per second only, it should start generating the power, right? This is the wind speed versus, that is the wind speed versus the power. So here, that the wind speed versus the distribution, that is the frequency distribution in terms of the percentage, right? At 3 meter per second only, it start generate. Remaining 50% of the time, there will not be generated any power from the turbines. So this I have explained to you. There is a pitch angle, angle of attack. Okay, the angle of attack is there is a chord line. It is a leading edge. This is a trailing edge. When you are joining the leading edge to trailing edge, this is called that is a chord line. Okay, that is a chord line. And angle of attack is there is a wind speed, wind, and the chord lines. So that's called that is the angle of attack. That is alpha. Right. So the blade motions, that is the plan of rotation. I mean, plane of rotation. This is the plane of rotation and the chord line. This is called that is a blade angle, beta. So that is a blade angle. So now just you can see there is a this is called that is a relative wind. Right. This is the undisturbed wind, and since the plane of rotation it is there, then it will make the relative speed of the blade and the wind. So that's called that is a relative wind speed. Now just look at here. So this I have explained to you, and it's happening the lifting and lifting action is happening there, right? Yeah. So this is the blade geometry I explained to you. So near the blade tip, okay. So near the blade tip, so resultant wind speed is very high. Now you can see the blade tip. I mean aerodynamic shape of the blade, right? Aerodynamic shape of the blade. So here the resultant wind speed is highest. So lift force per unit area is also very high. Okay, near the blade tip and closer to the hub. Just look at here. Stresses will be more on the blades here, because now you can see your hand, your extend your hand, entire hand. And also just have you ever read in the newspaper whenever the bowlers, so the bowlers always get pain on their shoulder. Why? Because they are continuously they are bowling, because they are giving there is a more stress, then that is a cyclic stress they are giving the blades also, because the blades mounted on the hub, it is experiences the very high stress. Okay, and blade performance depends on choice of aerofoil and what kind of aerofoils you have it. I mean the NACA series, National Advisory Committee for Aeronautics. Okay, NACA, NACA. So many number of families are there. You can also design your own families, choice of airfoils, and how the card and twist distribution is there, how the card and the distribution is there for the entire blade. So this will change the efficiency of the blades, right? Now just look at here the blade architecture. Okay, so this is the R by R. Okay, this is the R by R ratio, and this is the C by R. R is that is the length of the blade. Okay, this R is that is a small radius, right? Small radius of the blade, and R is that is the total length of the blade. Correct. So this is the card. C is that is the card by R length ratio. How it has to be distributed in a blade. So this is the maximum card. There is a maximum card that previously have seen the blades also. Now see, this is the root of the blade. This is the root of the the root of the blade. There is a circular cross section, and is slightly increasing the chord, right? Just look at here this blade and slightly increasing the chord, then it's reducing, then it's reducing. Okay, so the one more portion is there, the same kind of things you can just to see there. Okay, so then I also explained to you the stall control machine. The stall control machine, the stall control machine, just look at here how it is, the flow is attached. So when you have the stall control machine, so the stall control machine is attached to the Sir, is it audible?
Yes, sir.
Sorry, yeah, it was, I mean, internet disconnected. Sorry for
Yeah,
that.
yeah.
Audible.
Okay, okay, sir. Now, can you see my slides?
No, sir. Now you can share, sir.
No.
No, it's not sharing. No?
You can share, sir.
Yes, sir. Can you see my screen?
Yeah, yes, sir.
Yes.
Okay, okay, right, sir. Yeah, was disconnected. Yeah. Yes, sir. So this we have seen there. Yeah. So this is how we can power be regulated. So this is the flow is attached. I mean the flow is attached. When the wind speed is increases, the flow is detached. Okay. So that will happen. So this is the growth of wind turbine size. Now it is there in many size. Okay. Then now we'll come back for the design. So design methodology. Okay, earlier wind turbines are designed using sailing, so that I have explained to you for milling and grinding grains and various other purposes they have used. So these are the, I mean, the engineers, scientists who have developed the wind turbine. So, I mean, before 80s, it was not, properly designed, but it was designed. So initially it was designed for 12 kilowatt turbines. Okay, 12 kilowatt turbines, only turbine only, not for wind farm levels. It was not there. Wind farm means there is a many number of wind turbine, group of wind turbines were not there at the time, right, sir? So the Sumit Putnam wind turbine was the first electricity producing wind turbine, that is a 12 kilowatt. Then later the many scientists they will have keep on developed the various designs, and then finally now what we have it, that is an excellent technology. Right. But even though the technology has grown many things, but the basic structures are still it is common. Not much variation it is there. Right? Yeah. So this I have explained to you, that is the current practice of intermittent design, that's the conceptual design. What is the conceptual design? So then we should use the many standards. What are the different standards are being used? IEC 61400-1, this is the design requirements of wind turbine. International Electrotechnical Commission, International Electrotechnical Technical Commission. So this is the standard, and also in each country they are having the different their own standard for GL regulations. UK, so guidelines for certification of wind turbine. Denmark, they have their own standard for design of wind turbine structure, and for Netherlands, the NVN 11400. So Dutch standard for safety based on design of wind turbine structures. Germany, they are having their own standard. Okay, what is the conceptual? So the conceptual, that is a preliminary drawing. Then I thought, whatever, that is a free sketch. First, what you will do, whatever the design you want to do, you will make that is a free sketch. Okay, my structure is going to be like this. My structure is going to be like this. Okay, this is then make that is a overall layout. For example, if you want to know that is a wind turbine design, you will make that is a overall layout, how it is going to be there. Okay, my wind turbine is going to be 2 blade, or my wind turbine is going to be 3 blade. My structure is going to be there. Okay, so this is my structures. Okay, so this is called that is the conceptual design of the wind turbine. So it consists of major parts. Tower top components I have explained to you. What are the tower top component? What is the rotor I have explained to you, and the tower I have explained to you, and the foundation. So these are the major components. I am going to design it now. Conceptual design. Okay, so now I am thinking about where I have to keep my generator. Whether I have to keep my generator on the top, whether I have to keep my generator on the middle of the tower. So this whether the hub, where my the hub, what is the kind of the hub it is going to be there, what the kind of the nasal it's going to be there. That is the things, that is the conceptual. And also the various other conceptual designs are It's a rotor axis, whether it is a horizontal axis wind turbine or vertical axis wind turbine. Now you can see whether it should be the horizontal axis. I mean, the axis of orientation is that it means that the axis of orientation is parallel to the ground. So that's why the horizontal axis wind turbine, or it is going to be the vertical axis wind turbine. You can see here vertical axis wind turbine. Okay, here all the drivetrain components are placed on the top of the tower. Here all the drivetrain components are placed on the bottom of the tower. I mean that on the ground. So this is here this vertical axis wind turbine can extra. I mean can take the wind at any direction. Doesn't matter. But here the wind, when the wind direction changes, the entire rotor has to move towards the turbine. So here the advantage is that because the wind speed is increases with the height, the wind speed is increases with the height, the turbine also can be, I mean, it can go up to the higher height so that I can extract maximum energy from the wind. But here the disadvantage is I cannot go at a certain height, otherwise the buckling will happen. Okay, when you go to the higher height, the buckling, the stability, the structural stability will not be there. So that we cannot go. In the world largest turbine is 4 megawatt. But here the world largest turbine is now 14 megawatt. One single turbine, I'm telling. Right. So whether now the design options. Now I am going to conceptual design. I am thinking about now. See, in my mind it's going. So whether I want to design for horizontal axis wind turbine or vertical axis wind turbine. Now just I am going for whether I have to design for upwind turbine, whether I want to design for low wind turbine. So this is the upwind turbine means the turbine blade which faces the wind. Okay, but the turbine blades are lee side of the wind direction. This is the wind direction. It's facing the wind, but it's placed a lee side of the wind direction. Which one is that is the best? I have to think about it, right? So whether I want to go for single blade or two blades or three blade, which one is the best one for me? I have to decide. So based on the design, so whether I want to go for single blade turbine, the single blade turbine, I have to add that is additional weight on the opposite side. And also I have to when I'm doing the design of the press, I have to reduce the noise also. But when you are having that a single blade, you can reduce the two blades. But the thing is that it will generate the, I mean, large amount of noise. Correct. And the two blade, you can reduce the one blade, but I need there is additional mechanism here. There is a teetering mechanism. I have to place it here. But the only thing is the three blade is there is a perfect design. I can make it. So now I have to think whether I want to go for one blade, whether I have to go for two blade, whether I have to go for three blade. Now just think about whether I have to go for fixed speed turbine or variable speed turbines. Right. So fixed speed turbine is the turbine structure. This is the rotor, right? Is the gearbox will be the shaft, gearbox, right? The gearbox is coupled to the generators, right? So here the generator and the generator, then it is a grid, right? It's a grid, and in between the grid will have that is the reactive power combination. This is the capacitor bank. Capacitor bank will be here. Okay, rotor, gearbox, generator, and grid. Yeah, this is the capacitor bank. So this is called, that is a fixed speed turbine. The fixed speed turbine, irrespective of the wind speed, it always rotate at the constant speed or near constant speed. Exactly, not near constant speed. Okay, this speed is fixed by, there is a grid frequency. Our grid frequency, that is a 50 hertz. Okay, it will not allow more speed because it has been, I mean, controlled by the grid. Okay, so here you may ask the question, here is a small change in the torque, I mean small change in the torque, and large variation in the power will be there. So that is a fixed speed wind turbine. Variable speed wind turbine is, so the variable speed wind turbine here, the I mean it can vary the speed of the rotors. It can vary the speed of the rotor, because once the vary the speed of the rotor, and the generator rotor also can be varied, and the power fluctuation can be more. Okay, So the power fluctuation is the wind speeds in case the power also it will vary. Then efficiency of the variable speed wind turbine will be the higher than that the fixed speed wind turbine, right? So that is the advantages. Just you can see that simple and low cost induction generator for fixed speed wind turbine, and problematic drivetrain dynamics and fatigue loading. Okay, and poor power quality because it always consume the reactive power. So reactive power it will consume it, but in this variable speed wind turbine, reactive power compensation will be reduced because of the various frequency converter will be there in the variable speed turbines, and modulars are integrated. Now you can see the gearbox, number of stages. Then I have explained to you whether you want to use that induction machine, synchronous machine, direct drive machine for the generator. This is the conceptual. Is there so many conceptuals are there? Then you have to keep it in mind whether you want the low speed or high speed braking system you need, and also the tower. Which tower you want to go for it? Whether you want to go for that lattice tower, okay, then whether you want to go for tubular tower, or whether you want to go for the hybrid tower. Hybrid tower is both both the concrete and steel tower. Steel tower, this is a lattice structure. You can the lattice structure normal our electricity grid transformers. Okay, so the transformer lines will be there. This is a kind of structure, lattice structure, and this is a tubular structure, the steel roll. Okay, sometimes we will have the that is a hybrid structure, both the concrete. So concrete will be at a certain height. For example, 120-meter. I will have the concrete at 50 meters. 50-meter concrete, above which I have the steel tower. Steel tower, either I may have it, either I may have it the steel roll, or I can have that is the steel structures. And again, I'm thinking about the tower top components. What is the tower top components? What type of generator I have to use it? Whether either I have to use that is a synchronous generator, either I have to asynchronous generator, or either I have to use the doubly fed induction generator, whether I have to use the permanent magnet generator, or whether I have to what kind of hub I have to use it, whether I have to use the rigid hub or it's a teetering hub. It means depends on the number of blades and the base frame. What is the total mass it has to be decided. Okay, at what kind of component, based on this only I can design what is the load can withstand my top tower component. And whether whether then I have to think what is the capacity of the turbine. I have to decide whether I have to use such a 2 megawatt or I have to use such a 3 megawatt. So this we can design. So initially I will design, I will think, okay, I want to design my wind turbine either it's a 2 megawatt or 3 megawatt. Depends on this one, all other components will vary. Then tower, okay, the tower has to withstand all the loads, because the tower is, it's the freestanding structure. Okay, the freestanding structure. Then here you have, there is a cantilever structures, right? Then the tower has to withstand all the static and the dynamic loads acting. Okay, and the wind load also, the wind load it has to withstand. Okay, this tower which transmits the loads to the foundation. The foundation is to withstand all these loads. Then what I want to know that what are the loads acting on the turbine. Then that I have to know that. Then only I can design my turbines, right? That design my turbines, because the tower I have to design based on the wind, and also based on the rotors. How much it's a load going to act on the rotor, and how much load it's transferring to the my drivetrain, and how much on the tower top, and from this tower top how much the load it's transferring to my tower, and how much loads it's transferring my the foundation. So these loads we should know that, then only we can design the turbines, right? Then then conceptual design. Then if you have that as a experienced person, then he may know that. So previous experience it will help for him to design the further turbines, right? And also the regulations. What is the government regulations are there? Now the regulations. Grid code. That grid code, it should have certain limitations are there grids. Then the frequency should not go plus or minus 50 percentage of some limitations are there. If it goes beyond that, then they will give that there is a penalty. Okay, that grid regulations and market competitions. Okay, next, once now you have completed the all your conceptual design. So conceptual design, I have told you many conceptual, whether you want to go for horizontal axis, vertical axis, two blade, three blade, permanent magnet generator, synchronous generator, or you want to go for, what kind of asynchronous generator, synchronous generator, right? Whether you want to go for one blade or two blade, stall control or pitch controlled machine or active stall control machine. These are all your conceptual design. Okay, now it's okay. Then can you just simply design your wind turbine? No. Now the next thing is apply the numbers. Okay, what is the height? Okay, now you have the hub. Okay, now you have designed. Okay, you have decided to go for 2 megawatt, right? So 2 megawatt. What is the blade length I want? What is the rotor diameter I want? You know the power formula, power is equal to half rho A V cube. Rho A V cube into Cp. Cp you may take it that is a zero point 0.4, right? And rho, you know that rho, the density of air and the measured location, you know that area. Now you know the 2 megawatt. That is a 2000 kilowatt equal to half rho, for example, 1.12, right? Kilogram per meter cube. Area is equal to pi by 4 d square, okay, into v cube. Now I know the v cube, that is standard, is it 6.5, okay, 6 cube into zero point 0.4. What is the unknown quantity here? Only the d square. Can you now just calculate what is the d square now? From this you can find out what is the d square, and finally root of this values, then you will find out what is the d. Now we will find out what is the length of the blade. Okay, then you know the length of the blade, now you know that, right? So from this only, now you have the number you have given. At what hub height I want to go for it. Whether I want to go for 50-meter height, whether I want to go for 80-meter height, whether I want to go for 120-meter height. Okay, so this I have to decide. And also whether I want to increase the diameter also, that also can be done. I can keep it my 2000 kilowatt is the same. I can increase the diameter also. That is another way also I can do it. So the various, now I have to give the numbers, right? So the numbers mean how you can design. The various numerical modeling softwares are there, like, the Fast, Flux, SAMSF, and, yeah, that is a bladed various softwares are there. Just you can do apply the external condition, whatever the wind flow is there, apply to the load condition, what are the different loads are there, and also the structural model, carry out the structural model, and control system you have to design it, right? So numerical modeling, so preliminary estimate of the loads, then the numerical modeling, simply we cannot design it, then you know the preliminary load estimations. Estimation of load at this stage may involve the use of scaling of the loads from the wind turbines, right? The preliminary design must be evaluated. So once you have done the preliminary design, then you have to give to the third party to evaluate it. Whatever the things you have done it, then you have to do the evaluation. Without evaluation, it not be valid. How do you evaluate it? You have to give to the third party. And in addition, then it has to withstand for the extreme load conditions. Okay, numerical modeling. The category of loads of the wind turbine must withstand static load. You know the turbine, you know the structure of the turbine, the tower. I have the foundation, right? Static load. If there is no wind, simply it has to stand. One way is as the gravity load it will apply. Other one is that is the not associated with the rotation. Okay, then steady loads associated with the rotation. When the wind is there, will start rotating. Okay, then centrifugal force also will act, and cyclic loads due to the wind shear. Okay, the wind is here change in the wind speed. In the here the 5 meter per second will be there, here the 7 meter per second will be there. The cyclic load will be there, and short duration loads, and because of when the blades passing, see when the blades are moving, up and down, what will happen? The blades, when it comes in between the blades and the tower, because of its obstruct the flow of the wind, that will create some cyclic loads, that is the impulsive loads, and also stochastic loads, the short-term fluctuation. The fluctuation of the wind speed. The wind speed will not be always constant. It will vary the fluctuations. Okay, the short-term fluctuation, that is stochastic wind, and also transient load due to the starting and stopping. When I am doing the starting, I'm pressing the start button, I'm pressing the stop button, start and stop. When it's a start and stop, always the transient load will be there, and resonance induced loads will be there. So all these loads have to be taken care by the the numerical modeling softwares. Okay, so what we need from our blades, then always you have to design the optimization. Optimization means, then when you are designing your wind turbine blade, you have to do the optimization. Materials, yes, I have to do the materials compromise. When you are when you want to stitch your shirt, what is the size of the material you will take it? 1.2 meter, 1.3 meter, 1.4 meter, depends on the size of your body. Or will you just take simply for 3 meter? Okay, just 3 meter I am giving, and you please stitch for my shirt for half hand. Will you do it? No. And the tailor also will do, that is optimization, optimum utilization of the material, and he will stitch. If we give that is only 1.2 meter, he will stitch perfectly for your shirt. It means that he will reduce the waste, and perfectly he will. Have you ever seen, have you been to tailor shop? You can see how he is making it. First he will design. How he will design? He will take all measurement from you, right? What is the size, whether you want a half hand or full hand, what is the size, what is the width. Okay, that is the diameter. The width he will take it. Okay, what is for body length, body width, what is for length of a body, it's need that dress. Then he will make it exactly, he will make it on the pencils. Okay, or he will have the chalk he will make it, then he will cut. How optimum utilization of the material. The same way also here, what is the kind of material we are going to use it, we should avoid the wastage. Okay, and the minimum wastage only we have to do it. And aerofoil geometry. Okay, what kind of aerofoil geometry you are going to use it. And the loads, what is the kind of loads it's going to, and reduce the noise, and increase the efficiency, and reduce the cost. Okay, so that is the things we need. Low weight, and always should be stiff of the blade, and strength and durability is need, and aerodynamic design easy to manufacture and low price. So this is the procedures. And determine the rotor diameter. I have explained to you, power is equal to half rho AV cube. And choose the tip speed ratio. What is the tip speed ratio? That is called, that is the choosing, that is the tip speed ratio. So previously I explained to you, that is the blades, right? Right, the rotors. This is the rotor, this is the blade, right? This is the tower. Here you have the three blades. Yeah, that is the one blade. This is second blade. This is the third blade. Okay, this is the hub. Correct. These are the three blades, right? So tip speed ratio. Tip speed ratio means that is the efficiency. That is the CP. That is the power coefficient. The tip speed ratio. Tip here means the tip speed. Tip speed will be, higher than that the here wind speed. So in case the wind speed is 6 meter per second, that speed accordingly it will be maybe the 70 meter per second. At the tip, the speed of the tip will be the 70 meter per second. Your wind speed will be the 70 meter per second. So then 70 by 6, that is the tip speed ratio. The tip speed ratio only will decide your turbine performance. How? Here I say that the wind is blowing. Okay, when the rotor rotates very slowly, then all the wind which flows through the blade, between the blade, there will not be any generation. In case if the rotor rotates very fast, then it will act as a disk. Okay, then turbulence wind will be there, it will not generate any power. So then in mean, in between you have to decide at what speed it has to rotate. At what speed it has to rotate. That is the dispute ratio, that is the lambda. This lambda you have to decide which gives, that is the efficiency of your wind turbine. Then you have to design. So it has been already, many calculations have been done it. So for example, the dispute ratio should be, and for generating, for select an airfoil, the lambda should be less than 3. It is the curved plates. Okay, curved plates. You can see the lambda, and also the dispute ratio 8 to 24, 6 to 12, 3 to 6. Then you can design, you can select. And also, for when you want to do, there is a numerical calculation. Then your blade, okay, so this is your blade, the entire, this is your blade. Your entire blade has to be, divide. You have to make the grid. So mechanical engineers know that hyper mesh, you are meshing it, so that is a number of meshes will be more, right? So divide the blade elements into a number of small parts, right? And find the blade angles and the a part and calculate the performance, various things. Then okay, so this is the manual calculation, and all the inputs the number, then place it in the software. This is called, there is a bladed software. Okay, bladed software, the bladed software, then add all the numbers. Okay, you give, that is all the number. Okay, model analysis, wind turbulence, how much turbulence is there, and earthquake generation if there, aerodynamic information. Okay, whether it is a normal stop or emergency stop, and various conditions, many number of conditions we can iterate. So continuously you have to do the iteration. So almost more than 800 iteration we will do it for design of the wind turbines. And these are, the modeling. So the total number of blades, what is the tower height we need. Okay, this all these things we can give, because you have already that conceptual design, then you have done that is some detailed design. In this design you have given all the number, manually you have done the calculation. Now you are giving, because manually you cannot do the many number of iteration, it will take long time. Then you need the numerical modeling software. Then you can keep on change until you get, there is a optimum design, optimum power extraction, and optimum cost, right? Optimum power, optimum cost, and optimum materials, and all the things. Okay, from this just you can get it. The wind conditions. So the wind turbine shall be designed to safely withstand the wind conditions, correct or not? Okay, so the design value of the wind condition can be divided into two parts. One is a normal wind condition, other is a extreme wind condition. What is the normal wind conditions? Normal wind condition, it's normal. This is existing wind speeds are there. So which will occur frequently during normal operation of the wind turbine. Extreme wind condition means at the 50 years of the wind condition, what is the 50 years of wind, how it changed the wind condition. That is the extreme wind condition. So for the numerical modeling, then we have to analyze that the ultimate stress and the fatigue stress. The ultimate and the fatigue stress means during the power production, how it will be there, normal turbulence, how it will be there, normal turbulence model for extrapolation of the extreme events. Then you have to do, there is ultimate stress, fatigue stress. This is the normal conditions. Okay, this is the abnormal conditions. Okay, this will be there. And during the power production plus occurrence of fault, so fault may occurrence. Okay, normal turbulence model, extreme turbulence model, extreme coherent direction, coherence direction, extreme wind speed, wind shear. So all these conditions we will just check it during the power production plus occurrence of fault. Occurrence of fault, control system got failures, loss of electricity generation, then protection system has some failures, and the electrical fault conditions are there, and the external event for extreme operational gust wind speed. Gust wind means sudden change in the wind speed, sudden change in the wind speed. Okay, that is the extreme operational gust wind speed will be there, and normal turbulence models, control system, protection system failure, and during the startup how it will be there, during the startup, during the normal shutdown. Okay, so all these wind conditions will be examined. Emergency shutdown, sudden, all of sudden if you are doing the emergency, what are the problems we are facing there, and parked and fault conditions, and transport and assembly maintenance and repair conditions. So all these things will be put into the software, and doing the iteration for more than 800 times, so the iteration only, then you will get the wind turbine designs. And for numerical model load estimations, okay, you can just see, can see load estimation, how the load it is there on the turbine, whether it is extreme or it is a normal. So all these things, then you should know that. And controller algorithm. So you have to write the controller algorithm your own language, whether it may be the C language or it may be the machine languages. You can write your algorithm. So the algorithm is, the control system is to control the turbines. Why you have to control the turbine? At low wind speed, you have to extract maximum energy from the wind. At high wind speed, you should limit the power. And also the control system has to pitching the blades according to the requirements of the turbine, and yawing the turbines, then I told you, and maximize the power and minimize the mechanical loads. All these things have to be taken care by the controller systems, right? And this control system also, by using the bladed software, we can design it. First you have to do the manual design and keep on apply the loads on this one, right? And next, okay, once you have done it, then you come for the structural analysis. Okay, then how you will do that is a structural analysis. And for structural analysis, then you have to get input for I mean the load estimations. Now we have taken the load from the, there is a wind speed, because I have given there is a many cases. What is the normal turbulence model, what is the normal extreme turbulence model, extreme coherence direction, extreme wind shear. Okay, all this condition you have taken some outputs, right? You are applying to the structural designs. Okay, then load estimation. And where the load which is coming from, mainly from the blade root and the tower tops. I have explained to you blade root and I mean the tower top. I have the components, all the components, and the tower bottom loads. So all these loads. And structural designing is designing of any structure like blades, hub, nacelle, tower. Okay, and many commercially available softwares for the structural analysis. You have the ANSYS, you have the CATIA, you have the ProE and the SolidWorks for modeling and analysis, modeling and analysis. First, you are doing the modeling, the same like the mechanical softwares like CATIA, ProE, SolidWorks, and ANSYS for analysis. You can do it. Structural analysis, you can see there how where the structure is getting failure, where it is getting that is more turbulence, failures are there. Then you can add material, you can change the materials, you can increase the material thickness, whatever it may be, you can do in this analysis. Okay, many iteration has been done, load estimation has been done, structure analysis has been done. Then if the structure is okay, then you can go for proceed with the component designing. If it is no, then go for other iterations. So these iterations will keep on go until it says yes, okay, this component is okay. Then you go for the designing. Okay, design of machinery components. There are various other machinery components you can design it. Okay, pitch bearings, these are all the other components. Pitch bearing, pitch drives, yaw bearing, yaw drives, main shaft bearings. These are the machinery components, because the machinery components are the receptors of the load. Which one will receive the load? Because now you can see the bearings. Okay, here the blades, here I have the hub, the blade which is mounted on the bearings, right? Which is the receptor of the load. Now it is the bearing. First, bearing will receive the load and transfer this load to the hub. Then it goes to, that is the next bearings in front of the shaft. Then the shaft will carry the load. Then the shaft to, that is a gearbox. Then gearbox to the generator, and also the bottom. I mean gearbox to, that is a tower top. Tower top, that is the main frame, and the entire load will be transmitted to the main frame. The main frame will transmit the load to the tower, and tower will transmit the load to the bottom of, I mean the foundations. So this is the way the load will transmit. Okay, then yeah, this also explained. And design assessment. Once you have done it, now do the assessment of the designs, right? From the stage of numerical modeling to component designing. Numerical model. So you have completed the numerical model. Now go to the component designing. Okay, the documents and mathematical models are provided to a third party. They will do the assessment evaluation. Once the evaluation is there, then you have that is a perfect design, right? So various third party agencies are there. They will vet the design. Entire design will be vet by the third party. Now make the detailed engineering drawing. Okay, all the turbine components. Once you have vetted the design document, then go to that is the engineering, detailed engineering of the turbine component. Okay, and 2D drawings. Okay, 2D drawings, you might have seen if at drawing classes you will make that is a 2D drawings, right? And you generated, and then you do go for that is a 3D. Okay, this is a detailed engineering. You have carried out the detailed engineering of the gun, then make the prototype. What you do it now? Once the detailed engineering has been made, now you can do the prototype model. You have to develop it. Now you can see that the model has been developed based on my design. Model has been developed. So okay, once the model is developed, can I go for directly for generating power? No, you cannot do it. Now we again you have to do the testing and get the certification. Now you have to do the testing means we will place so many instruments, like for strain gauge. We'll place the strain gauge for each and every locations. Okay, tower, each and every location will take the load from there and do the analysis. Either any problem is there doing the testing. Okay, if there is no issue, then we can go for the next stage. Not only for the testing, and also we check the power quality. Okay, now just look at here the load measurements as per the IEC 6140013, and the safety and the function test, whether it is properly the safety is there in this turbine, and the function, all the functionals. Okay, then it will be checked during the testing. So it will take for all the wind conditions. Okay, all the wind conditions, it will be testing will be carried out. The test location has to be as per the international standard. Up to 200 meter, there should be a testing area. Okay, and also the testing area should be okay. Okay, as per the standard, or it's going beyond that, whether it is bearable by the man, or the mankind, or it's not. So these are the test will be carried out. Okay, and once the test is carried out, it will be after successful completion of the type testing, the measured loads were compared with the theoretical loads. Measured load and comparing with the theoretical loads, whatever I have done it. Okay, so during the numerical modeling, then once the both are it's okay, then go for certification. Then certification body will certify. So once the measured loads are found to be within the design load, then a type certificate is issued to the turbine model. Okay, then once the type certification is issued, then you can go for large production. Then large production, right? Right. Okay, so what are the challenges when you face it? Because the construction cost, time, risk, and grid. Okay, then grid and operations cost per year, and constraint, whether the grid availability, surge capacity, maximum power storage, physical area, height, where you are going to get the area, what is the height, whether it is obstructed by the neighbor, what is the topography, whether it is a flat terrain or complex terrain, what is the atmospheric conditions, whether you have the sufficient fund for time, what is the NPV, what is the loan, what is the regulatory, environmental permission, safety, supply chain, whether it is availability of the supply chain. Once you have installed the wind turbine, you need the supply chain. It means that the continuous for various supply chains you need logistics. Okay, so and also the latest nowadays, the turbines are okay, turbines are, the advancement means that it's decreasing the specific power and mass specific torque development, advanced controls and the load reduction, and drivetrain configuration is completely it's changed. Okay, so now you can see there. So now I already said, so while you are designing the wind turbine, then I told power. So power of the turbine is equal to half rho A V cube. Okay, so now in India, then Indian condition is city. Okay, in Indian condition is most of the location we have that is a low wind speed. I mean, that is a moderate wind speed in terms of moderate wind speed. But I want to extract that is always energy from that is a moderate wind speed. What I have to do, I have to increase my area, right? Now I increase my area. So increase my area mean, and also at the same time, the weight of the turbine should not be increased. The weight of the rotor should not be increased. So that's why the mass of the rotor should be that is a 0.145 times of 1 into length cubic of 3. I mean 2.9. Okay. In this connection, then you have to, I mean, maintain the weight using normal, I mean, the scaling laws. The weight of the wind turbine blade should increase with the length of the power of 3. Length of power of 3. So this condition it is there then, but the nowadays it has not been crossed to 2.2. It is been that excellent conditions, then we are maintaining it. Just you see that when you are designing, not only taking care of the single parameters, we have to see the so many parameters. Simply we cannot increase the rotor size, simply you cannot increase the weight. Okay, such various laws we have to do it. Now we can see this is the world largest wind turbine, that is a 12 megawatt. One single turbine, the height is that is a 260-meter hub height from the ground, that is the 260-meter, and one single blade length is 107 meters. Okay, so it means that 220-meter rotor diameter. But now the latest 14 megawatt turbine is 260-meter rotor diameters. Imagine it, 220-meter, 260 meters rotor diameter, almost two cricket ground. Two cricket ground. Imagine it, two cricket ground means you cannot imagine. So such a kind of turbines. So the wind turbine is it is multi. I mean the multi branch, right? So it consists of civil, mechanical, electrical, civil, mechanical, electrical control systems, computer science, all things it's involved. Okay, that is there. So it has been already installed by GE, right? That is the specific power we have to reduce it. So decreasing the specific power. So specific power means that is a capacity by swept area. That is the things and the capacity. Now I have the 2000 kilowatt, only 2 megawatt capacity. My swept area I have increased. I mean the pi by 4 d square. So diameter I have increased, for example, 200. I mean, yeah, diameter I have increased for 120 meter. For example, just I am telling 120 meter for by 4. So 30 into 3.14, that is a 2000 kilowatt. Now you can see. So I can increase the rotor diameter so that I can keep my generator, the capacity is same, so that it can increase the capacity utilization factor. So initially the capacity is 28 percentage. Now it has reached to 36 to 38 percentage of capacity utilization factor at the same capacity of the turbine, but increasing the diameter of the blades. So this is also possible. That is a decreasing specific powers. So increasing specific powers. Yeah. So that is there, and also just you can see specific power is decreases. Initially it was where it was very high. Now it is almost 400 watt per square meter specific power. Now it has reduced to 230 watt per square meter. Right. So the wind turbine classic classes of wind turbine: class 1, class 2, class 3 wind turbine. So it depends on the reference wind speed and turbulence. Based on this only we design the wind turbine. So design the wind turbine, and also 1 year return wind speed and 50 years gust wind speed what will be there, right? So this is the reference wind speed. In case the class 1, this is the high windy locations. class 1 wind speed location, there is a 50 meter per second we will take it, and 50-year gust wind speed will take it to 70 meter per second. So just think about what was our different storm we received, Varda fuel and Oki fuel. It has not even reached 70 meter per second. It was there 55, 45 meter per second only. So 45 meter per second, but I have designed my wind speed is 70 meter per second. It can simply can withstand. So there is a class 1 wind, there is a class 2 wind 42.5 meter per second, and a class 3 wind speed is 7.5 meter per second. So this is the base case to design your wind turbines. Right. Yeah, these are the references I have taken. And so this is the digital wind farm. Nowadays, to increase the efficiency of the wind turbine, there's the digitalization, it's happening there. Every data, okay, every data are being, sent to the controller. The controllers every second it's checking, and it's keep on checking it. And, and also the digitalization of the softwares are there, and we are doing the analysis for every second, and if there is any issues or problem is occurred, immediately it is being attended and rectified, so that it's increase always efficiency of the wind turbine. So that's called the digitalization of the wind farm and the wind turbine, it's happening there. Yeah, thank you sir, thank you for listening. If you have any question, please ask me, sir.
So participants are requested to unmute
So this
yourself
is
and clarify your doubts.
doubts. Any participants, both mechanical, electrical, control systems, and civil engineering? And if you have any questions, may please ask. So no doubt. Any questions, sir? Question, madam? So almost 44 participants are. I'm very happy. So I'm very happy to deliver. I hope I have not made you too sleepy and make bored. Actually, this is whatever the maximum information I have provided to you. And it may, and we cannot understand 100%, and you may understand whatever things it is there at, at the minimal level. And when you are going to teach or design your wind turbine, then definitely it will be helpful. Oh, that time the Bhupati has taught me these are the things. Okay, I hope you have learned many things from this lectures. Thank you, sir. And once again, I would like to thank the organizers and for inviting me to give this lectures, and also the management for providing the opportunity, and also the participants, the staff. I mean, most of them are staff I know. So how many of them can sit and understood for the 2 year? I mean, the 2 hours of the lectures. And once again, thanks for all listening to my lectures. Yes, sir. Still,
Thank you,
participant,
sir.
any question?
Participants are not asking any questions, sir. So thank you, sir, from organizers side also for accepting our invitation and sparing your valuable time with us and sharing the large information to the participants, which may be helpful while designing of their turbines, wind turbines. So they can share the information to their students also. So thank you, sir, once again.
Thank you, sir. Thank you. Thank you all. Thank you. Thank you for listening once again. Thank you, sir. Yeah.
Yes. So this is the morning session. So all of you join at 2 o'clock for the session by Professor Mangu. He is going to deliver a talk on introduction to power evacuation strategies from solar photovoltaic energy systems. So thank you, one and all.